Hello, chemistry students. This is Professor Sean McMahon with Chapter 11, our second lecture on acids and bases. With our first lecture, we did review of nomenclature. We gave some examples of our neutralization reactions, and we introduced, instead of just the basic definitions of Arrhenius, the Bronsted-Lowry definitions for acids and bases. And with the Bronsted-Lowry definition of acids and bases, we defined a base as a proton or hydrogen ion acceptor. So in the example here, I have hydrogen chloride in water, and I see in this reaction, and with the Bronsted-Lowry definition, you have to look at the entire reaction to see where the transfer of the hydrogen ion takes place. I can see that a hydrogen is transferred to the water, and that transfer shows us that water is accepting this hydrogen ion and is acting like a Bronsted-Lowry base by that definition. I also see from last time that there really isn't just a hydrogen ion by itself. And I know we write it out with neutralization and net ionic reactions, but there really isn't just a hydrogen ion. In reality, the hydrogen ion is the hydronium ion in solution. And we see this nicely when we see the full balance equation of a Bronsted-Lowry acid-base reaction. So we see that the water becomes this hydronium ion because the acid, the hydrogen chloride or the hydrochloric acid, donates its proton. And it results in what's referred to as a conjugate acid. So the base now becomes a conjugate acid, and the acid becomes the conjugate base. And we also touched on the conjugate acid-base pairs and how if we have a weak acid, we have a strong conjugate base. So in this case, the hydrogen chloride or the hydrochloric acid is a really strong acid, completely dissociates 100% of the time. We also talked about that because we have our 6 strong acids, and hydrochloric acid is one of them. So this conjugate base is extremely weak because it doesn't want to accept the proton from the hydronium ion and go in the reverse direction. That's why we see the arrow going in one direction. We also notice that we're going to measure using the concentration of our hydronium ion. We are going to determine the acidity of a solution. And that's what this lecture is about. This lecture is determining pH by using the formula negative log hydronium ion. Okay, so that's how we measure how acidic a solution is. We're measuring the hydronium ion. Okay, the brackets, if you remember from earlier talks, means molarity. And molarity is moles per liter. So if I have more hydronium ion, I'm going to be a more acidic solution because water accepted the hydrogen ion from an acid that donated it. We also talked about that water can also behave as an acid. Now, ammonia is a very weak base. Okay, so this doesn't happen a lot. And we see this with the double arrow right here. It's showing that it's a reversible reaction. It's also showing that the ammonia is a weak base. But what we notice is that the base becomes a proton acceptor, and the water can actively donate a proton. So when we see this donation, now the water is behaving as an acid. Okay. Now, the hydroxide ion that's left behind once the water donates the proton is how we measure basicity. So we can measure basicity based on this hydroxide ion concentration. So that's kind of what this lecture is about. How can we measure how acidic or basic a solution is? And what we show is that if I put an acid in water, water behaves as a base. If I put a base, even if it's weak, okay, if I put a base in water, now the water behaves as an acid. So that makes water amphoteric. So that essentially is the starting point of this lecture. Water is amphoteric, and that means it can behave as an acid or a base depending on what it's around. If I'm around an acid, I'm going to behave like a base. If I'm around a base, I'm going to behave as an acid. Well, I showed this in the previous slide. I have an acid, it's behaving as a base. I have a base, it's behaving as an acid. What happens if I have pure water, though? Can water actually react with itself? So could one water molecule behave as an acid and the other behave as a base? And the answer to that is, yeah, believe it or not, water can self-ionize. So what do I mean by that? Water can actually react with itself. It doesn't happen a lot, okay? This only happens about 2 out of 10 billion, or 10, that's 10 million, I'm sorry. It only happens out of 2 out of 10 million. Now, that doesn't seem like a lot, and it's not, but it is something that we have to take in consideration. So what happens is I can have one of the water molecules donate a proton. And when it does that, I actually produce the hydronium ion. So they kind of switch this up and now becomes the conjugate acid. And I have the hydronium ion. And the acid that donates the proton becomes the conjugate base, the hydroxide ion. And remember that I had said that we measure acidity based on the concentration of the hydronium, and we measure basicity based on the concentration of hydroxide. Well, if I have pure water, and I know that this is in equilibrium because I have a double arrow, that means I have a forward and reverse reaction. It also means it doesn't happen a lot, right? Mostly in the water, it only happens 2 out of 10 million. So the bulk of water would just be the liquid water molecules. But there is a small fraction of hydronium and hydroxide. How small of a fraction? Well, if I think of it as there is 1 out of 10 million, right? If one hydronium is 1 out of 10 million, there's also 1 out of 10 million of hydroxide. But let's make it easy because there's a lot of zeros there. I'll just say 10 to the 7th, right? There's 1 out of 10 to the 7th. Now, let's make it easier. And we don't like having exponents in the denominator. So really, if I wanted to bring this exponent into the numerator, if I follow my rules of exponents, I would just make it negative. So really, I have 10 to the negative 7 hydronium ions and 10 to the negative 7 hydroxide. Because it's a 1-to-1 ratio, this is neither acidic or basic, because how I measure acids, which is the hydronium ion, and how I measure bases, hydroxide, it's a 1-to-1 mole ratio. So this is a neutral solution. Plus, the bulk of the solution is just the water molecule. So in pure water, this ionization, right, produces a small quantity of these 2 ions, but it produces them in equal amounts. And what are the amounts? I just showed you 10 to the negative 7. So the concentration of the hydronium and the hydroxide are equal. And it essentially is there's 10 to the minus. So if I was to write this out, there's 1 times 10 to the minus 7 moles per liter of each, because that's what the brackets mean. The brackets mean molarity. And if it's happening roughly 2 water molecules out of 10 million, I produce 1/10 of a millionth, which is 10 to the negative 7 molarity of each. So we know that the molar concentrations are equal, right? And we also know, because of this, that there's equal amounts of how we measure acidity and basicity. Now, why is that important? Well, we learned in chapter 10 that we can create an equilibrium constant, right? We can write out a K. And if you remember our K of equilibriums, right, they were products over reactants And if there were coefficients, we would put them as exponents. And also, we would only incorporate, because during equilibrium, we're looking at the phases that change dramatically. We're only incorporating gases and aqueous solution and aqueous ions. So in pure water at 25 degrees Celsius, there's a very small amount of this hydronium and hydroxide. We said it's 1 times 10 to the minus 7. Now I can write an equilibrium constant for that reaction earlier, and I can specifically give it a name, because this is very important. We use water a lot in chemistry. It's the, major solvent. So when we think of solutions, we think of water-based solutions where water is a solvent because it's so abundant. So there's a very specific K of equilibrium. We call it the water equilibrium constant. And essentially the reason why we're only writing the hydronium and the hydroxide is, if we go back, remember there were 2 water molecules giving me 1 hydronium ion and 1 hydroxide ion. So if I follow products over reactants, my products are the hydronium and the hydroxide. The reason why I don't incorporate the reactants in the water equilibrium expression is because it's a liquid, right? So their concentration doesn't change drastically. I went from, let's say, 10 million water molecules to 10 million minus 2. That's still not a big significant change. However, if I look at it from the perspective of the hydronium and hydroxide, if I initially only started with water and eventually I have 1 of each, well, going from 0 hydronium to 10 to the minus 7 moles per liter, that's significant, going from the, so that is the equilibrium. And again, this can go back and forth. We could have the reverse reaction take place, but for every hydronium and hydroxide that react to do the reverse reaction, then 2 more waters will reestablish that equilibrium. So we always have that constant. And why is this important? Well, we can create an equilibrium constant at 25 degrees Celsius and basically take the concentrations of each of these under these equilibrium conditions, and we can calculate at 25 degrees Celsius, water's equilibrium constant is 1 times 10 to the minus 14. Why is that? Because if we follow our rules of exponents, 10 to the minus 7 times 10 to the minus 7, well, with the rules of exponents, you just add them, you get 10 to the minus 14. Now, why is that important? Well, it provides us a scale of, okay, can I determine acidity or basicity? So let's say I add a bunch of acid into solution. And if I add a bunch of acid, if we look at that earlier slide, I'm producing hydronium ion. And I could just kind of refer back to the very first slide where I had the hydrochloric acid. I add it to water. When I add it to water, what do I produce? The hydronium ion, which is the conjugate acid to the base, and I produce the chloride ion. So what happens? I produce more hydronium, right? So the hydronium goes up. Well, a lot of students don't understand is, why does the hydroxide go down, right? Why doesn't the hydroxide stay at 10 to the minus 7? It makes sense that the hydronium is increasing because the hydrochloric acid is reacting with the raw water, and the water is behaving because it's amphoteric, like a base and a subset becomes a hydronium ion. But why does the hydroxide go down? Well, that goes back to our neutralization reactions that we learned in earlier chapters and in solution chemistry. If I add the hydrochloric acid and it reacts with, let's say, some of the small amount of hydroxide that's available, because it may come in contact with that, what do I produce? I produce water, because now this is my base accepting the proton, and I produce the chloride ion. So by adding hydrochloric acid and acid to pure water, the hydroxide now decreases. So what we see is there's this inverse relationship. Hydronium goes up, hydroxide goes down, and we leave that neutral state of 10 to the minus 7 where they were in equal amounts. Now, why did this occur in the first place? I threw a bunch of acid in it. So it increases the hydronium, which means now I'm going to have a value greater than 10 to the minus 7. Maybe it's 10 to the minus 3, right? So don't forget, when we have negative exponents, really 10 to the minus 7 is like 0.1, 2, 3, 4, 5, 6, 7. That's not a lot of moles, right? That's my molarity. If I'm, let's say, at 10 to the minus 3 now, that's 0.001 molarity. That is a higher concentration than this. So remember, even though 7's bigger than 3 in magnitude, the negative 3 is actually a larger concentration because we're getting closer to 10 to the 0. And if you remember, anything to the 0 power is just 1. So this would be a 1 molar concentration of the hydronium ion. We also see that hydroxide decreases. So this might be like a 10 to the minus 10. So there's even more leading zeros because it's even less concentrated. It's the same concept with base. If I add a bunch of base, right, what's going to happen? Hydroxide. So if I add, let's say, sodium hydroxide to water, it's a strong base. It's going to completely dissociate in the solvent, which is water. And I don't even need to write the water in this equation because water is not really reacting with anything. I just throw the base in water, and because sodium is a group 1 element, it completely dissociates and gives me a bunch of hydroxide ion. So what does that mean? Well, now the hydroxide increases. Well, if the hydroxide increases, it's more than 10 to the minus 7. Why does hydronium go down? Well, same thing. If I add sodium hydroxide to the hydronium ion, okay, what's going to end up happening is the hydroxide is going to be neutralized, right, to produce H2O, and I'm actually going to produce 2 H2Os and a sodium ion. Now, this might be hard to see because this course, we don't do a lot of shortcuts like that, so I'm going to make it a lot easier. If I throw sodium hydroxide, I know that there's just going to be a bunch of hydroxide ions. So really, the sodium is always soluble and it becomes a spectator. I'm going to go ahead and erase that and just do this. So now I don't even need to worry about the sodium. Okay. And what I can see is when this donates the proton, I get 2 water molecules. Right. So this is behaving as an acid. This is behaving as a base. I protonate this, and now I have 2 neutral water molecules. Well, what did I do? I got rid of the hydronium acid and formed its conjugate base, which is just neutral water. So my hydronium concentration goes down. So why is that important? Well, based on this inversely related relationship, I can determine whether something's an acid or a base just by looking at the hydronium and hydroxide concentration. When they're both 10 to the minus 7, they're equal in water at 25 degrees Celsius, and it's considered a neutral solution. When I increase acid, so if I throw acid, hydronium goes up, hydroxide goes down. So this becomes more acidic because the hydronium ion, if I look at this inequality, is greater. And then the inverse, if I add a bunch of base, hydronium goes down, hydroxide goes up, it's a basic solution. Now, why is that important? Now, remember, we're saying that the concentration is 10 to the minus 7 molarity. What is the pH of a neutral solution? The pH is equal to 7. What is the range of acids and bases? Well, pH 0, pH 14. Those are your ranges. 0 to 7 is acidic. 7 to 14 is basic. Where am I getting the 14? Well, if you remember with the Kw, which is always your hydronium times your hydroxide, and we're going to use, that at 25 degrees Celsius. If they're both 1 times 10 to the minus 14, it should always equal 10 to the minus 14. So even when it's in acidic condition and this goes up, goes down, it's still going to equal 1 times 10 to the minus 14. So kind of talked about this. If I add acid, hydronium goes up. If I add base, hydroxide goes up. However, because they're inversely related, the Kw, the water equilibrium constant, will always equal at 25 degrees Celsius 1 times 10 to the minus 14. And that's very powerful. That's very powerful. Now, why is that powerful? Well, because we can always use Kw to calculate, if we have one, the other one. So again, in a neutral solution, what do we see? 1 times 10 to the minus 7, 1 times that is 1 times 10 to the minus 14. Now, in an acidic solution, why is this acidic? Well, 10 to the minus 2 is a lot bigger than 10 to the minus 12, right? And remember, with that negative exponent, 10 to the minus 2 is 0.01. I don't even want to write out 11 zeros, because that's what that would be. It'd be 11 zeros followed by 1. So I don't even have room. That's actually why we use scientific notation. But we can clearly see that 10 to the minus 2 is a lot larger. So what does that mean? Well, if there's more hydronium, it's got to be acidic. Well, how did I get 10 to the minus 12? Because I used Kw. 1 times 10 to the minus 2 times what number would give me 1 times 10 to the minus 14? 10 to the minus 12. And again, I see here, this is 10 to the minus 5. This is 10 to the minus 10. This is bigger. This is acidic, right? If I go here, this is basic. Why is that? Well, 10 to the minus 8 is less than 10 to the minus 6. So now the hydroxide is greater. Just like 10 to the minus 11 is less than 10 to the minus 4, the hydroxide is greater. So that is basic. But they all add up to 10 to the minus 14. It's really easy when there's a 1 in front because it's a base of 10. So students don't have difficulty. Like if I told you my hydronium is 1 times 10, what's a number I didn't use? I don't know, -3. Students are really good and they'll be like, well, that's easy. This is 1 times 10 to the minus 11. Why is that? Well, because if I take this and I multiply it, it's 1 times 10 to the minus 14. And how come? Because rules of exponents. I add the exponents. -3, -11 adds up to -14. However, it's always a base of 10. It's a little bit trickier when I don't have a base of 10, like here. So a lot of students will say, well, 5 times 10 to the minus 11, if I times that by 2 times 10 to the minus 4, minus 11 and minus 4 gives me, and this is true, 10 to the minus 15. That's correct. What they're not seeing is 5 times 2 gives me not 1, but 10. So it's not giving me 1 times 10 to the minus 15. It's giving me 10 times 10 to the minus 15, because 5 times 2 is 10. And 10 is 10 to the first power, right? Because 1 is 10 to the 0 power. And 1 plus a -15 would equal 1 times 10 to the minus 14. So that's the beauty with Kw. It always equals 1 times 10 to the minus 14. If you don't understand how I use rules of exponents to determine that, that's okay. No one's forcing you to do that. You can just use your calculator and punch it in, always using your Kw, and your Kw always equals whatever the hydronium concentration is and the hydroxide. However, I recommend using your scientific notation button, which is either EE, EXP, or the times 10 to the X. So let's try one. What is the hydronium concentration of a solution if the hydroxide concentration is 5 times 10 to the minus 9? So what do I need to use? Well, Kw. I know Kw is a constant. it's the hydronium times the hydroxide concentration, and it always has to equal 1 times 10 to the minus 14. I want to know what the hydronium concentration is. I have the hydroxide, so I want to know what, and it's red too because it's acidic. But so what do? I plug in what I know. I know that Kw is 1 times 10 to the minus 14. They give me the hydroxide concentration. And now I just divide both sides by the hydroxide concentration. And what do I get? My hydronium concentration is 2 times 10 to the minus 6. Now, 2 times, why is there 2 sig figs here? Well, 5.0, I'm not using Kw. Kw is a constant, so it's an exact number. I don't use it for significant figures. However, the hydroxide concentration that was given to me, the 5.0, is 2 sig figs. And this is where we really think the zeros, that trailing zero in scientific notation lets me know that there's 2 sig figs. So I have 2 sig figs here. The other thing is, now, is this an acidic or in a basic solution? Well, let's take a look. We said hydroxide concentration was 5.0 times 10 to the minus 9. So which one is bigger, 10 to the minus 6 or 10 to the minus 9? 10 to the minus 6. So this solution, if you were asked, is acidic. Why? Because the hydronium concentration is bigger than the hydroxide. Now, some of you are good, and before even plugging in your numbers, you may just right off the bat rearrange this algebraically. You might have just said, well, Kw equals hydronium concentration times hydroxide. And if I'm looking for hydronium, I'm just going to divide both sides by that. So I'm going to get Kw divided by my hydroxide is my hydronium. And then you could plug in your numbers. Either way is fine. You could first plug in the numbers and then rearrange the numbers, or algebraically first manipulate the equation to solve for hydronium. It really doesn't matter. You get the same answer. So now, if lemon juice has a hydronium concentration of 2.0 times 10 to the minus 3. So even before I solve this problem, what does that make lemon juice? Well, if the hydronium concentration's minus 3, that's more than 10 to the minus 7 where it's neutral. So if I have more hydronium than a neutral solution, then this is going to be an acid. And that makes sense because what do we know about lemons? They're sour. Why are they sour? Citric acid. So lemon juice is quite acidic. But the problem wants you to find the hydroxide concentration. So how do we do that? Kw. We're looking for hydroxide. I have hydronium and a constant. I plug in the numbers, 1 times 10 to the minus 14, 2.0 times 10 to the minus 3, divide both sides, and what do I get? Hydroxide is 5 times 10 to the minus 12. I'm sorry, I've noticed that this version of my PowerPoint did not put the exponents up. So I apologize, I should have double checked that. In my other computer, it actually had it properly, and then when I transferred it to this one, it doesn't. But I think you probably figured that out. So this brings me to the topic of the pH scale. And I kind of already introduced this, and we use the pH scale to determine whether something is acidic or basic, right? If it's a 14, it's strongly basic. If the pH is a 0, it's strongly acidic. Really, typically, acids are considered very strong if they're between 0 and 2. They're weakly acidic from 2 to 7, because 7 is neutral. To be a strong base, typically your pH is between 12 and 14. If you're between 7 and 12, you're weakly basic. So that's just a general way of saying, hey, this solution has this pH. Oh, it's a strong acid, it's a strong base. You can use the number of pH to tell you that instead of using the hydronium concentration and the hydroxide concentration and comparing. It's a lot easier to have one number, pH, instead of having both concentrations and then comparing to determine whether it's acidic or basic. So how do we come up with the number of pH? Well, I wrote it earlier. It's the negative log of the hydronium concentration. And now, if you're not used to using logs, most students are, but you're going to have to use the log function. That's why you always use a scientific calculator, and you can't see because I'm on blur, but there's a log function on your calculator, and you'll be using. So if a pH is less than 7, I know it's acidic because, 7 is 0. If it's more than 7, then it's basic, right? So 14. And if it's 7, it's neutral. Now, a lot of people get confused. They're like, well, if it's 14, that's bigger than 0. Why is that acidic? Because remember, we're going to be doing the negative log, and the exponents, the magnitude 14 is bigger than, let's say, 2, but it's a negative exponent. So if we go back and look, right, 10 to the 0, right, is a pH of 0, but this would be 10 to the minus 14. If I look 10 to the minus 7, right, each of them are 10 to the minus 7, that's a pH of 7. Where am I getting these numbers? I'm using kW. So we see if hydronium concentration is 10 to the minus 1, and this is minus 13. 10 to the minus 2, minus 12. All of these, what they're omitting is the 1 times 10 to the minus, okay? But I can clearly calculate any of these by just using pH is equal to the negative log of a hydronium concentration. So if I was to pick 1 times 10 to the minus 5, when I calculate this, my pH, and you can do this on the calculator, when you take the log of 10 to the minus 5, right, you'll still have the negative in front, but log base 10 on your calculator, 1 times 10 to the minus 5 is going to give you a negative 5 if you hit that on your calculator. And then the negative becomes a positive 5, and that's how I get that number. And where do I get the 10 to the minus 9? I used my kW, right, which is hydronium times hydroxide. And if I rearrange this to solve for the hydroxide, I would get kW equals, or divided by hydronium, equals my hydroxide. And I know kW is always 1 times 10 to the minus 14. And if this is 1 times 10 to the minus 5, if I follow my rules of exponents and I'm doing a division, what do? I subtract. So hydroxide would be 1 times 10 to the minus 14 minus a negative 5, which is like adding 5, and that becomes 10 to the minus 9 right there. So if the base is a 1, you can do this in your head. It's not always 1, so that's why, if you have your calculator, you'll be using that. But I like to show, everyday substances, because your acids and bases, and, people have these visions of, oh my God, this is dangerous, and within reason. So I like to show that, okay, well, drinking water is slightly basic, right? We have some ions, some carbonate ions dissolved in there. Blood is slightly basic, right? It's 7.4. It's almost neutral, but why is it slightly basic? Well, we're going to learn that in the next lecture because of the bicarbonate ion is a weak base. Detergents, right? Cleaning products typically are slightly basic. So we see detergent, we see salt water, antacids, Windex, cleaning materials, bleach, and then lye is a very strong base. So you see that in things like liquid Drano. That's why that's not really good for you have the old galvanized pipes. You have the old pipes. It's not really that good for them, okay? What is acidic? Well, a lot of the things we consume, that's why there's a big push for alkaline water, is a lot of the things we consume are slightly acidic, okay? So what is that? Well, milk, bread, right? Oranges and orange juice, a carbonated beverage because you have, carbonic acid because the CO2 being dissolved and the reverse reaction of water and CO2, or carbonic acid decomposing to water and CO2, is them combining to produce carbonic acid, right? Then vinegar is acetic acid, and there's lemon juice. Gastric juice essentially has your hydrochloric acid to help denature proteins and to activate pepsinogen to pepsin. But this is in everyday products, okay? So don't be afraid of acids and bases. They're fine. You deal with them every day. Not that you were afraid. Okay, so significant figures are a little bit different with pH calculations. Why is that? With pH calculations, whenever you use log, because remember, to calculate pH, it was the negative log of the hydronium concentration. The way it works is when you look at a concentration, we're just looking at these numbers, right? So this is 1 sig fig. With log rules for sig figs, because it's logs, you count after the decimal. That's just a rule. And the reason why we use log as a scale for pH to make it easy, it's a lot easier to say the pH is 12 than 1 times 10 to the minus 12. It's not uncommon to use a log scale. We use it for the Richter scale to measure earthquakes. That's why, you know, a 7.2 and a 7.4, there's a drastic difference. Why? Because it's base 10, it's a log scale. It's the same thing with pH, right? So we have to take into account the precision after the decimal to get a better understanding of the acidity. So that's why with log calculations, you use the sig figs after the decimal. So here I have 1 for the concentration, because we follow the normal rules like we've always been doing. But because of pH in the log, I have 1 number after. Here in the concentration, there's 2 sig figs, 8.0. So what do? I go 2 sig figs after the decimal place. Over here, the concentration, 2, so I go 2 sig figs. And it's that precision that we need after the decimal to really distinguish the pHs, because we're using a logarithmic scale, and it's more significant when we get to the tenths and hundredths. We need to really look at that. So let's do a calculation of hydronium from pH. And really, you can do that by doing what's called an inverse log. Okay, that's essentially what you're doing. But what we're doing is we're going to calculate the hydronium from a pH of 3.80. So how do I do that? So to convert the pH to a concentration, I'm going to do a second function key and do the inverse log button. So you're going to see log on your calculator, and then above that log, you should see a 10 to the X key. That's what we're going to do. So how do we do this? You're going to hit inverse log, right? My calculator is a little bit different. So inverse log, and you should see the 10, a caret in parentheses. And then you're going to enter negative 3.80. Okay, so negative. Don't hit the minus. I actually, by accident, just hit the minus. Look for the negative button, 3.80, close parentheses. And you know, when you do this, you're going to get this number, 1.5849, blah, 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 times 10 to the negative 4. However, how many sig figs? Well, remember, with pH, because it was a log function, we go after the decimal. We only want 2 sig figs. So it's going to be not 1.5, because we look to the right, it's an 8. It's going to end up being 1.6 times 10 to the minus 4 molarity. So what is the hydronium concentration of a solution with a pH of 2.85? Now, you never have your exponents for your final answers in a decimal form, okay? Because really, to figure this hydronium concentration out, you actually do have to go on your calculator. You have to go second function or shift, inverse log, and type in negative 2.85. But you can't leave that as a final answer. You'd have to hit equal because the exponent has to be either the 3 or the 2. So when you do that, you end up getting 1.4 times 10 to the minus 3. Now, how can we make sense of this? We know if we had a pH of 2, that would equal 1 times 10 to the minus 2. If we had a pH of 3, that would be 1 times 10 to the minus 3. So we see that this is a full difference of 10, right? Because 0.001 molar, 0.01 molar. So 2.85, what is that? Is that closer to 3 or 2? Well, it's closer to 3, and that's why we have that. So if you wanted to do deductive reasoning, you could use kind of that understanding and be like, oh, it's got to be the -3 because it's closer to 3. It's not 1.10 to the minus 3. It's 1.4 because it is slightly more acidic. It's 2.85, but you can just use your calculator. That's a lot easier. I'm just showing you if you want to use deductive reasoning. So what is the hydronium concentrate? What is the hydronium concentration of tomato juice? If it's 2.12 times 10 to the minus 4, what is the pH? Oh, I'm sorry. We're just figuring out the pH. So to do pH, if we remember, it's a negative log. Okay, so on your calculator, you're going to type that in. So you could hit negative log and then type in the hydronium concentration. So you would go negative log 2.12 times 10 to the minus 4 on your calculator. And then you're going to get 3.674. The reason why you want 3 sig figs is, again, the rules for logs is it starts after the decimal. So there's 1, 2, 3 sig figs here. So you have to go 3 sig figs after the decimal. And my answer would be the pH of tomato juice is 3.674. So it's close to 4, because 1 times 10 to the minus 4, but it's a little bit more acidic because 2.12 is more than 1. So this is a little more hydronium concentration, a little more acidic. So it's closer to 3. It's moving towards 3. Okay. However, what if I give you the hydroxide concentration and I want pH? Not a problem. I know pH is negative log hydronium. Then give me hydroxide. I can solve for the hydronium. How? Kw. I know Kw equals hydronium times the hydroxide concentration. Kw is a constant. I use my hydroxide concentration. I underline this to show there's 2 sig figs. I solve for the hydronium, rearranging this, and I get my hydronium, 2 sig figs, is 1.6 times 10 to the minus 12. I can now plug that into this formula. So pH is negative log 1.6 times 10 to the minus 12. Remember, because this is a log function, my final answer, I count the sig figs after the decimal, 11.80. Why? 2 sig figs after the decimal. This makes sense. Why does this make sense? Because 1.6 times 10 to the minus 12 is less than 6.3 times 10 to the minus 3 molar. That was our hydroxide concentration. So that means the hydroxide is a greater concentration. So this is basic, and 11.80 is basic because it's between 7 and 14. It's almost a strong base, right? Because it would be a strong base if it was 12 to 14. So can we do, what is the hydronium concentration of the following solutions if I give you pH? Of course, we can use that inverse log that I was talking about. So what do? I go into my calculator, I hit second function or shift, log, I should get the 10, the caret, and then I put a negative 3.7 and I get 2 times 10 to the minus 14. Why is there only 1 sig fig for the concentration? Well, for the pH, there's only 1 sig fig after the decimal. And I know to get pH, it's a negative log function of hydronium. So the pH, I count the decimal, I count the sig figs after the decimal. So there's only one sig fig. Well, what about if it's a pH of 12.331? Same thing, inverse log, plug that in. And the reason why there's 3 sig figs is there's 3 sig figs after the decimal, so there's 3 sig figs for the concentration. So that's kind of the calculations, you know, for pH and hydronium and hydroxide concentrations to compare them to see whether it's acidic or basic, but it's a lot easier to just figure out the pH. Now, there is something called POH. The way that works is your pH plus your POH equals 14. And that's because the KW is 1 times 10 to the minus 14. And your hydroxide is 1 times 10, let's say 1 times 10 to the minus 7, and then your hydronium. And remember, what do? Right? -7, -7. We add the exponents to get -14. Well, that's what we're doing. Whoops. We're adding the pH and the POH. So for any of these, if we have the pH as 3.7, I could easily figure out the POH by subtracting 3.7 from 14, and I would get my POH is 10.3. Very easy. Or if you really want, you can get the POH by simply doing a negative log of not the hydronium, but of the hydroxide. So if you were to plug in, you know, your hydronium concentration, you could into a negative log, you can get POH. For this particular course, I don't do that. For those of you that are watching that are not in this course, there is a really easy way to get POH using a negative log of hydroxide, or just saying pH plus POH is 14. So that's an option for you, for other students. Now that we're done with pH and KW calculations, just as a reminder, you know, we've actually done single displacement reactions where we throw acids or throw a metal in an acid and it displaces the hydrogen gas. We've seen this. So we review this. There's a lot of review in chapter 11 of acid-base chemistry with our reactions like the double displacement neutralization, the single displacement with a metal and an acid to give us hydrogen gas, right? Then there's the solution concentration, molarity, and things like that. So the nomenclature, that's why I'm reviewing. It also, for those of you in my lecture, helps prepare for the final, right? So we've seen this. We add magnesium to an acid and it bubbles and it releases, this is actually an exothermic reaction, a lot of heat, and I produce the metal salt, which is a magnesium nitrate in this case. I think in my lab, we used the hydrochloric acid, so you would have been given the magnesium chloride, but you would still produce the hydrogen gas once you threw the magnesium in there. We've also dealt with acids and carbonates, and we saw that in the double displacement reactions, when we throw acids with carbonates, it produces carbonic acid, but the carbonic acid is an unstable intermediate in the presence of other acids and breaks down and decomposes the CO2 in water. So we saw this in our home labs where we take calcium carbonate as a solid and add hydrochloric acid. If we did the double displacement, right, if you do the do-si-do, you get your calcium, which is 2 plus, carbonate, which is 2 minus, your H plus and your Cl minus. We do the do-si-do, we see we would get carbonic acid and the calcium chloride. However, because this is in the presence of an acid, a stronger acid, the hydrochloric acid, the carbonic acid doesn't like it, it decomposes. What does it decompose into? Water and CO2 gas. So the full reaction is actually this. It's a double displacement coupled, right, with a decomposition. That happens a lot in biochem. Reactions are coupled with other to give them the power or the driving force to get the desired result. In this case, we're producing CO2 and H2O. We also see this with bicarbonates, right? One of the protons, right? So one of the protons or two of the protons are going to produce two of the bicarbonates, right? So I'm going to end up getting a sodium sulfate. The reason why there's two sodiums, it's an Na plus and sulfate is an SO42 minus. The two hydrogens are going to react with the bicarbonates, producing the two carbonic acids, which then decompose the two waters and two CO2s. So why am I doing this? In the acid-base chapter, they expect you to be able to predict products for acid and base reactions. The nice thing is, if you're in my course, this is a good review for the final, because this is like chapter, 5 stuff, right? Where we actually saw a reaction. So here I have a metal in the presence of an acid. So because this is an element and this is a compound, this is a single displacement. The zinc displaces the hydrogen to produce a new element, the hydrogen gas, and a new compound, the zinc chloride. This should be review. If it's not, it's okay, but it's good review for the final because we do have to predict products in reactions so that we can do stoichiometry, because the first thing you need in stoichiometry is a balanced chemical equation. Let's try the acid in the presence of the bicarbonate, right? So if you're a little stuck, what could you do? You could say magnesium's 2 plus, the bicarbonate is a -1, or the hydrogen carbonate. I got an H plus and a Cl minus. What's going to happen? I'm going to do it, right? When I do, I should get magnesium chloride, and I should get carbonic acid, and I would get actually 2 of those. That's because I have the 2 H pluses and the 2 bicarbonates. However, we know that the bicarbonate, or the carbonic acid, the carbonic acid as a product is an unstable intermediate in the presence of the strong acid, and it should decompose. What does it decompose to? Well, water is always the result of these unstable intermediates in aqueous solution. It produces water, and what's left over? If I subtract H2O from H2CO3, what's left over? Just the CO2, and that's your gas, and there's 2 of them. So that would be my final answer. So what if it was just carbonate? Yeah, same concept, right? We're going to do H plus, NO3 minus, crisscross. I'm going to produce what? Carbonic acid and sodium nitrate. It's always soluble. I'm going to put a 2 there to balance it because I have 2 hydrogens to go with the 1 carbonate, and I need 2 sodiums and the 2 nitrates. So there you go. So I end up getting that. However, again, the carbonic acid is an unstable intermediate in the presence of this stronger nitric acid, and it decomposes to H2O and water. So we talked a little bit of a review of the metals in acid to give us the single displacement reaction to produce the hydrogen gas. We talked about the double displacement reactions producing carbonic acid, which is an unstable intermediate in the presence of other acids, and decomposes to H2O and CO2. Now we're just going to go back to the simple double displacement with acids and bases. And again, we got hydroxide, we got the hydrogen ion, which really is the hydronium, but to make this easier, we do the double displacement and we produce, sodium chloride in the water. That's why I always had students, right, when I break this down, write it as HOH, because it just made it easier to balance, okay, if it wasn't a 1-to-1 mole ratio. But we also, because it was an aqueous solution, we could do the net ionic equation. So this is a nice review of that. The chloride cancels the sodium because they're on both sides, and my neutralization reaction has a net ionic equation of the proton and the hydroxide giving me H2O. Now, in reality, like I said, there is no free hydrogen. It's attached to a water, so it's really the hydronium ion and the hydroxide giving me the two H2Os. So can we do this? Can we do a double displacement, right? And predict products? Yeah. H plus, CO minus, aluminum's a 3+. How do I know that? Periodic table. I could also see there was 3 hydroxides, and hydroxide's a -1. So I crisscross applesauce. I get aluminum chloride, and there has to be 3 of them. It's aqueous. Plus water, I'm going to write it as HOH, liquid. And why do I write it as HOH, liquid? Because now I need to balance this. And what I see is, if I balance metals, I have 1 aluminum, 1 aluminum. And then I go to non-metals, 1 chloride, but I have 3. I need to put a 3 here. Then I see I have 3 hydroxides, only have 1 here, 3. Saving hydrogen for last, 3 hydrogen, 3 hydrogen. I'm balanced. So you should be able to do the next one as well, right? With the barium hydroxide and the phosphoric acid. If I was to break this apart, I got the barium 2+, the hydroxide. How do I know barium's a 2+? It's an alkaline earth metal, group 2. I'm going to put the H+ in the phosphate. I'm going to crisscross. So I'm always going to produce, a water. And what else? Well, now, because I have the barium, which is 2+, and the phosphate, which is a 3-, when I crisscross, I need 3 barium and 2 phosphate. And this would actually be a solid because phosphates are always insoluble. Solubility rules. It's not a nag, sag, Castro bear. So phosphates are insoluble. And then when I look at this, okay, and the reason why this is aqueous is group 7A is soluble with the exceptions of lead, mercury, silver, and aluminum's not one of them. But going back to this, now I need to balance it. So I would do the barium first. I have how many barium here on the reactant side? 1. I have 3 here, so I put a 3. Then I would go to the non-metals, which I'll treat the phosphates. There's 2 phosphates here. There's only 1, so I'd put 2 there. Then I'd probably go to the hydroxides. There's 1, but 3 times 2 is 6. And then that makes sense because I would go to the hydrogens, and 2 times 3 is 6. I'm balanced. That would be my equation. So that is lecture 2 of acids and bases, where we introduced our calculations for pH using Kw to determine hydronium and hydroxide concentrations, and using the formula pH is the negative log of hydronium. We also reviewed, because I wanted to break up some of the calculations, we reviewed a lot of the acid-base reactions. The reason why I'm reviewing the acid-base reactions is, if we notice, all of these acid-base reactions are going to be in solution. So in our next lecture 3, we're going to do solution stoichiometry and revisit what we learned in chapter 9 and perform more solution stoichiometry calculations, but specifically, or a little more specific, with the reactions involving the acids and the bases. So I want to thank you for watching. Thanks for your patience, and I'll see you next time.